Let's look at another example where we're determining the electrostatic energy for a continuous charge distribution. And the example I have in mind is a sphere. It has a total charge capital Q, and that's distributed uniformly in this spherical volume of radius capital R. So we're going to try to find the electrostatic energy for forming this sphere. We're going to use three methods. The first is to get the work done to build up this sphere layer by layer. We're interested in the work done to carry charge from infinity to build this sphere. The second method will be to evaluate the volume integral, and that's integral over all space of the electrostatic field energy. And so that's equal to little u sub e, which is equal to epsilon 0, the E field squared divided by 2. Just to remind you, this integral will be over the space outside of this charge density and also inside. The third method will be to use the charge density and the potential, and because this integral will disappear wherever this is 0, it only includes the part where we're in the sphere. That'll be a simplification. So let's look at this layer by layer buildup and evaluate the work done, or the electrostatic energy when we're finished. So I want to remind you that the increase in electrostatic energy by bringing in a dq from infinity to a point where the potential is V, that increase is equal to that potential times the charge that you brought in. And we derive this for point charges and for blocks of charge density ρ. So to build up the sphere by these infinitesimal layers, which we're going to carry from infinity, we need the potential at the surface of the sphere of radius little r, containing a sphere of charge density ρ. At this point here, where we have a sphere of radius little r, what is the potential right here? Well, if you remember, the potential at the surface of such a sphere at radius r, we'll call V sub r, is equal to a point charge Q sub r located at the center, where little q sub r is the charge inside this sphere. That comes about because of spherical symmetry. So if we write that down, then the potential of a point charge is kq over r, and so this is the charge inside that little sphere, and so this is the potential at the surface of that sphere. So building this up, we need to calculate the dq. We're producing a new layer of charge. We're bringing in spherical shells just to save integrating over the angles. We're adding a spherical shell. The dq is the charge density times the volume of that shell. The volume of that shell is just the surface area of the sphere at that particular r times the thickness of the shell, so that's the dr. Once we have V and dq, we can form the product to get the work done. We're going to bring dq into this potential. The change in the electrostatic energy will be V of r times dq. Just to remind you what ρ is, it's the capital Q over 4/3 pi r cubed, capital R. The little q is just the density times the volume of that inner sphere, which is 4/3 pi r cubed little r, and dq is just the charge density times the volume of the shell. We've got V sub r in terms of little q, so let's put it in terms of ρ by using this expression here. We substitute little q of r, and so we end up with the potential at radius r equaling this quantity here. As you would expect, as you increase the radius of the sphere, you're adding charge, and so the charge inside is increasing, and so the potential increases accordingly. The increase in the stored energy is equal to this. Let's put in V sub r, that's right here. Here's V sub r, and then here's the dq right here. This will be the differential change. If we integrate, then we'll get the total electrostatic energy. It's the integral of this quantity here, and the only variable is r. Our integral is over r, and if you look here, we have r squared times r squared. The little r dependence is right here, r to the 4th. The quantities out here are just collecting all the constants. It's interesting that you have, for example, ρ squared, and that comes about because the energy will be proportional to the charge squared, or in this case, ρ squared. Doing the integral, we get capital R to the 5th over 5, and so multiplying together what we have here, this is the electrostatic energy of producing this total sphere of capital R, and in this case uniform charge density rho. We can rewrite that in terms of Q by just substituting back in our charge density, and so that's Q over the volume of the final sphere. Putting that in here, so here's the first part of the constants, here's the second part, this was rho squared, R to the 5th over 15. Canceling out different constants, we end up with this as the electrostatic energy of forming that sphere of total charge Q, capital radius R. And just one more time, in terms of rho, I've already done it, it's up here, and I've just repeated that. So this is the same equation that we have above. Now let's use the electrostatic energy density, which is U sub E. For that we need the field, because remember the energy is equal to epsilon naught over 2 times E squared, so we need the field. We need it both inside and out. The outside is actually easier. We just take all of the charge and put it at the center of the sphere, which we can do because of the spherical symmetry. So it's just the Coulomb type E field, which is kq over r squared. Inside, it has a different R dependence because as R increases, we get more charge. If we do that calculation, which we've done before, we just have K capital Q little r over capital R cubed. As you increase R, the E field has to go up because there's more and more charge being included inside that sphere. The E field increases linearly with R. To find the total U sub E, we have to integrate little u sub E over all space. This integral here is the electrostatic energy density inside times dV. This is the outside term here. So they look similar, but obviously the limits of the integrals are going to be different. So inside we're going to go from 0 to capital R. Here's our epsilon 0 over 2. Here's our E inside squared. And then here's our dV. And I think you can see what we have out here is very similar. Putting in our E inside, that's given by this quantity here. We square it. Epsilon 0 over 2, and here's our d tau, the volume element. And then we do the same thing for outside, and so the only difference will be this E field outside. Bringing out all the constants, for the inside contribution, we have this set of constants. And you'll notice that we have r squared times r squared, so we get r to the 4th here. So we got an integral that's going to give us r to the 5th. We group the constants over here, and we integrate 1 over r squared. And here we integrate from the surface of the sphere out to infinity. And so that'll be a contribution for doing the work from outside to the surface of the sphere. Let's do the integrals, and so I've done that here. We have the set of constants here that are common. We have a 4 pi in each case. Now we have the ratio of 1 over r to the 6th, which comes from squaring this 1 over r to the cubed, times the integral of little r to the 4th, which gives us this quantity right here. For the second integral, we get 1 over r, which when we put the limits in, we get 1 over capital R. The value at infinity would be 1 over infinity, so that drops out. Making the combination of these, we end up with this set of constants. Adding up what's in the brackets, we have 6 over 5 times 1 over r. So you'll notice here we have a 1 over r and a 1 over r, so that gives us this quantity here. Again, making simplification, I'm going to keep 1k, and I'm going to change 1k to 1 over 4 pi epsilon naught. So that's where this came from here. Why? I want to get rid of some of this pi epsilon naught dependence. Again, the brackets are the same. Simplifying this, then, you'll notice that this is just 1/2, so we end up with 3 little k q squared over 5 capital R. And that's exactly the same as we got in A. If you take this and do our transformation to rho, you obviously should get the same thing. We want to now do the third method, which is using rho v over 2. And so first we're going to need the potential inside. Realize that's all we need in terms of potential, because this is the case where we only care about where this is non-zero, and that's inside the sphere. First, I want to just redo the derivation of V inside, and I'll do that quickly because we've done this before. The easiest way is to integrate the E field from infinity to little r, where r is less than capital R. From lots of symmetry arguments, we still have the fact that E outside is equal to this, and E inside is equal to k q sub r over r squared in the r hat direction. So this is actually the way you start to derive the V that we used last time. This is putting all of this charge at the center of the sphere and just calculating E. What is q sub r? Well, we've already got that. It's the capital Q over the volume of the inner sphere divided by the volume of the total sphere, and that will give us the charge that is inside the small sphere, and that's Q little r cubed over capital R cubed. So using that for our little q, we can get the E inside, and so we write that down like we would expect to have kq over r squared. The kq times this is the q inside, and so that simplifies to this, and so again we have E increasing with little r. To determine V inside, we have to integrate from infinity to r, the minus sign, in terms of the E field E, and that's E dot dr. But remember, this has two components. It has E outside and E inside. So we have to break down the integrals into two parts. The first part brings us to the surface of the big sphere, and then the second part gets us to the radius, a little r. So if we put that in, we'll have the integral from infinity to capital R here. And remember that dr and r can be taken parallel to each other. And then we have the E inside integrated from capital R to little r. The sum of these two will give us the potential at the little radius r. And again, these are parallel. Doing the integrals, we'll have, for the outside value, we'll have kq over capital R. And then we have the inside contribution, which is proportional to r squared. And so then when we put in our limits, in this case here, see we've already integrated this one here because we're familiar with that. This is outside. And this one's inside, and so now we have to evaluate the limits, which is capital R to r. Putting those in, we get two terms right here. This then gives us the potential inside, which is kq over 2 capital R times 3 minus r squared over capital R squared. And that's just combining all the terms that you see here. Now we're ready to do our calculation of the electrostatic energy using rho times V. And so we're only going to need V inside because that's the only region where rho is not equal to 0. Here's our V inside that we've derived. It's equal to this quantity here. We don't use V outside, and so we put that into our electrostatic energy. The integral is 1/2 times rho V integrated over the volume of the sphere. We'll put in our 1/2, we'll put in rho, we'll put in our kq over 2r, 3 minus r squared over r squared for our V inside, and then here's our d tau, our friend 4 pi r squared dr. So separating out most of the constants here, our integral will be from 0 to r of 3r squared, where the r squared comes from our volume element, minus, now we have r to the 4th in this position divided by r squared, and we're integrating over dr. Forming the integral, we'll have the constants here, 2 pi k capital Q rho over r. The integral will give us r cubed over 3. The 3 will be canceled out here. And then the second integral will be r to the 5th over 5. You'll notice that when we cancel the r's, we're going to get an r cubed over 5. To simplify that, we get 4/5 times r cubed. Going back to our constants, we have 2 pi and then kq times rho. Well, rho is just capital Q over the total volume. Simplifying all this, I think you can readily do that. We end up this expression, which is the same as what we got in the earlier versions. And just for completion, if you transfer this over to rho, you get, of course, the same u sub b in terms of rho.